the section 3.4 lecture video on graphs of polynomial functions. So today we're going to look at basically how the equations of polynomial functions are related to their graphs. So the first thing here is just a review of things we've already looked at. So the graph of a function f of x is symmetric about the y-axis and is an even function if f of the opposite of x equals f of x. And one of the things we can remember is this word even is really important, because if all the terms have even exponents or are constant, then it was an even function, right? That's something we mentioned when we first encountered these in the functions chapter. The graph of a function f of x is symmetric about the origin and is an odd function if f of the opposite of x equals the opposite of f of x. And if you remember back to the function chapter, if all the terms have odd exponents, then it's an odd function. Okay, and therefore it's symmetric about the origin. And then the last option is anything that's quadratic has an axis of symmetry, and that axis of symmetry is at negative b divided by 2a. So if we look at these examples here, we should be able to tell fairly easily if they have symmetry, and if so, what kind. So this first one's a polynomial, and if you look at their exponents, we've got an exponent of 6, 4, 2, and then a constant term. So that means this is an even function, which means it has y-axis symmetry. The second example here has an even, an odd, and a constant term. So that means it's neither even nor odd, but it is quadratic. So that means that it has an axis of symmetry at x equals negative b over 2a. So in this case, b is 10 and a is 5. So this is x equals negative 1. The third one here, the exponents are 5 and 1. So that means this is an odd function, which means it has origin symmetry. The fourth one here has an even exponent and an odd exponent. So it's not even or odd, and it's not quadratic. So this one has no symmetry. And the last one here, you need to multiply out to make sure what kind of symmetry it is. So if we do that using the box method, this is x squared minus 1, x squared minus 1. X squared times x squared is x to the fourth. X squared times negative 1 is negative x squared. X squared times negative 1 is negative x squared. Negative 1 times negative 1 is 1. So this is x to the fourth minus 2x squared plus 1. So that's an even term, even exponent, an even exponent, and a constant, which makes this an even function, which means it has y-axis symmetry. Okay, so that's just reviewing some of the symmetries that we've talked about in previous sections. We can also talk about what happens at the x-intercepts for graphing functions. So what happens at the x-intercepts has a lot to do with what the multiplicities are. So if a real zero has an even multiplicity, then the graph does not cross at the x-axis. So that would look like something like this. If this is the x-axis and there's my x-intercept, we just touch it and bounce off. Well, let's try to draw that a little better. Okay, like that. If it has an odd multiplicity, then it crosses through. So it'll look something like that at its x-intercept. So you can work at this either one of two ways. You can either use the algebra to see what the graph looks like, or you can use the graph to see what the algebra looks like. So if I set this function equal to 0, right, to find the x-intercepts, I can factor out an x squared. That leaves me with x minus 3. So we get x squared equals 0 and x minus 3 equals 0. So we get x equals 0 and x equals positive 3. Now, because this was x squared, this has a multiplicity of 2, right? We learned that in the last section. And this, because it was to the first power, the x equals 3 has a multiplicity of 1. So that means we have the x-intercept 0, 0, and 3, 0. And at 0, 0, it's got an even multiplicity, so that means it does not cross. So it's going to look something like this. And for 3 equals 0, it has an odd multiplicity, so it does cross. So it's going to look something like this. And we could check to see if we did that correctly by graphing the original function. So if I open my ClassCalc app, and I get rid of what we were doing last couple times ago, and we graph y equals x to the third power minus 3x squared, we'll see that we get exactly what we expected. At 0, 0, we have an x-intercept, but it doesn't cross. And at 3, 0, we get an x-intercept, but it does cross. Okay, so the same thing can happen here. Okay, we can solve this one. So we set it equal to 0. And now there's a couple different ways you could go about this, but you could add 16 to both sides. And then we could use the square root property, because the square root of x to the fourth is x squared, and the square root of 16 is plus or minus 4. So we get two equations. And then we could use the square root property again. So x equals plus or minus 2, or x equals plus or minus the square root of negative 4, which is 2i. So there's a few interesting things that happen here. First of all, I have 4 roots, and I have a degree of 4, which means all of these have a multiplicity of 1. So we are going to cross the x-axis at any x-intercepts, and I only actually get 2 x-intercepts. I get 2, 0 and negative 2, 0, because these are not real numbers, plus or minus 2i. So they are not x-intercepts. And so because the multiplicity of all of these was 1, is going to cross. So these does cross at this x-intercept, and it does cross. And once again, you can check by drawing the graph of the original function and see if you got what you expected, which it does cross. So I do y equals x to the fourth minus 16, and we get 2 x-intercepts, negative 2 and 2, and the graph does cross at those, so we get exactly what we would expect. So go ahead and pause the video for a second and try these other 2 problems on your own, and when you push play again, we'll go through them together. Okay, so now you've had a chance to give these a try. We can go ahead and go through them. So set it equal to 0 and solve. So we have 2 things multiplied together to get 0. So we can break that apart into 2 pieces and solve them individually. So this would be x minus 1 equals 0, so x equals positive 1, and x plus 3 equals 0, so x equals negative 3. And because this was x minus 1 squared, this has a multiplicity of 2, and because this was x plus 3 squared, this also has a multiplicity of 2. So we get the x-intercepts 1, 0, and negative 3, 0, and in both cases, it does not cross, because they're both even multiplicity. And if you graph that, that's exactly what you'll see. You'll see that you get these 2 x-intercepts, and in both cases, it just touches the graph. Then the last one is a quadratic that we can solve by factoring. So we need 2 numbers that multiply to get negative 6 and add to get negative 5. So we've got 1 plus negative 6, which is negative 5, and 2 plus negative 3, which is negative 1. So the first one works. So this is x plus 1 times x minus 6 equals 0. So x plus 1 equals 0, and x minus 6 equals 0. So x equals negative 1, or x equals 6. And notice both of these have a multiplicity of 1, because they were both not raised to a power. So those are odd multiplicities, so that means negative 1, 0, and 6, 0 my x-intercepts, and it does cross for both. And if you were to graph that, that's exactly what you would see. Okay, so that's how multiplicity plays a role in x-intercepts. Now, another thing that plays a role in the graph is the leading coefficient. So if our polynomial looks like this, the leading coefficient, remember, is the coefficient on the term of highest power. So the value of that coefficient has a lot to do with what the graph looks like. So there are basically four options. So a sub n could be positive, a sub n could be negative, n could be even, and n could be odd. So if a sub n is positive and n is even, then if we plug a number into this, what's going to happen is if we plug a positive number in, we're going to raise it to a power, so we'll get a positive number. And then if we multiply it by a positive number, we'll just get a positive number. So the right-hand tail of this graph is going to go up. If we plug a negative number in, a negative number to an even power is positive. A positive number times a positive number is positive, so this would also go up. Then if the leading coefficient is negative, well, if you remember back to transformations, a negative leading coefficient just reflects the graph across the x-axis. So since both tails were going up here, when I changed the leading coefficient to negative, they'd both go down. Now, if we do the same thing with an odd exponent, if we plug in a positive number into an odd exponent, we get a positive number times a positive leading coefficient would make this go up. And then a negative number to an odd exponent is negative. A negative times a positive leading coefficient is still negative, so this one would go down. And then if we change the leading coefficient to negative, it just reflects this across the x-axis. So it would look like that. Now, one of the interesting ways to talk about this idea of these, what happens in these tails, is to talk about what's called a limit. So the notation lim x arrow infinity, sorry, not infinity, x arrow a of f of x is read as the limit of f of x as x approaches a. And so the idea is, what value does the function get close to? What do the y values get close to as x goes to a certain place? So for example, if we look at n odd and a, well, let's actually just do these in the order that I drew them up here in the graph. So the first example we did in the graph is n even and a sub n positive. So that's this one. So as x goes to the right forever, what happens to the y values? Well, as we go to the right, the arrow goes up. So that means as the x's go to infinity, so do the y's. And then as x goes to a negative infinity, as we go to the left, the function goes up, the y's go up. So as the limit as x goes to infinity of f of x, also, as x goes to negative infinity, f of x goes up. So it goes to positive infinity. And then if we look at n is even and a sub n is less than 0, that would be this example here. Notice that both tails go down, so both of these limits are going to be negative. And then if we look at the odd one, so if we look at the first one here that matches up to the bottom left graph, as x goes to infinity, the y's go up, so that's positive infinity, and as x goes to a negative infinity, the graph goes down, so that would be negative infinity. And then if we look at the last one, these just get reversed. Right? Because as x goes to the right, y goes down, so that's negative infinity. And as x goes to the left, as x goes to negative infinity, the y's go up, so that's positive infinity. So that's what happens in general. But now let's look at some specific cases. So for example, here, if we wanted to find the limit of that first function, one way to do that would be to graph it. So if I graph y equals negative 3x to the fourth plus 9x squared what we want to look at is what happens as x gets really, really big. Well, as we make x get bigger, as we go to the right over here, we're looking at this right-hand tail, and the right-hand tail is going down, which means this limit is negative infinity, because the graph goes down as we go to the right. So this means to the right, and the graph goes down, so this means down on the right-hand side. So in the next one, we're doing negative infinity, so that's to the left. So if we look at y equals x cubed minus 5. If we go to the left side of this graph goes down. So on the left-hand side of the graph, we're going down, which is negative infinity. Okay, so why don't you all take a second. This next one would be to the right, because we're looking at positive infinity, and this one would be the left because it's negative infinity, and decide what you think those limits are. Okay, so now that you've had a chance to try those, if we look at the right-hand side of this graph, the graph is going up, so that's going to be positive infinity. And if we look at the left-hand side of this graph, the left-hand side goes up, so this one is also positive infinity. Okay, so that's the idea behind limits. Now, the last couple things we want to be able to do with this section is we want to be able to use what we've just talked about to pick out matching graphs, and we also want to be able to solve inequalities using this idea. So let's start with matching the graphs. So when you go to match up graphs, there's a few things you want to look for. So first of all, we can look at the leading coefficient. So a sub n, in this case, is -2, which is a negative number, which means the right side goes down. Okay. We can also look at the exponent, the leading exponent, the degree of the polynomial. In this case, it's 1, which is odd, which means the tails go in opposite directions. Okay? And one last thing you can do is you can find the y-intercept or the x-intercepts. In this case, the y-intercept is pretty easy to find. If you plug 0 into the graph, you get 1 out. So if you look at all of that information and you go down here and you look at the graphs, do we see anywhere the right side goes down, the other tail goes in the opposite direction, so it would go up, and the y-intercept is 1? Well, if you do that, you should get 2 that might be answers, E and G, right? The right-hand tail goes down, the left-hand tail goes up, and they both have y-intercepts of 0, 1. So there's one more key that makes us know that this is E, which is that this graph is linear, and E is a linear graph, whereas G is not. Okay, so we could try another one of these together. So if we look at the next one, we could talk about the same thing. So a sub n is equal to -2. So we know the right side goes down. Right, same as the last one. N is even. So n is 2, which is even, which means they go in the same direction. So the left side also is going to go down. Right, because they go in the same direction. And then we have a y-intercept of 0, 1. So we look for a graph where both the left and the right side are pointing down, and the y-intercept is 0, 1. And when we do that, the only one that matches that description is A. So the answer to this one would be A. Okay, and then if we try one more together before I have you all try the rest of these. In this next one, a sub n equals -2, so the right side goes down. N is 3, which is odd. So that means the left side goes the opposite direction, so left side goes up, and we have a y-intercept of 0, 1. So of the ones that are left, that would only leave G. Right side down, left side up, intercept of 0, 1. So this one is G. So go ahead and pause your video for a second and see if you can figure out, match up the other 5 equations with the remaining 5 graphs. Okay, so now that you've had a chance to try that, let's go ahead and go through them together. So a sub n for this one is -2, which means the right side goes down. N is even. So that means the left side goes the same direction, so left is also down. And this has a y-intercept of 0, -1, right? If I plug in 0 for x, these first 2 terms go away, and I'm just left with -1. So which graph do both tails go down and has a y-intercept of -1? Well, that's F. Okay. The next one, if we do the same things, A sub n is -2, which means the right goes down. N is 4, which means the left goes the same way as the right, so it also goes down. And we have a y-intercept of 0, 6. So that would leave us with B. For the sixth one, A sub n is -2, which means the right goes down. N is 4, which is even, so that means the left goes the same way as the right, which is down. So the ones that were left where they both go down really only leaves us with H. And we can tell it's H because the y-intercept would be 0, 0. So that's this one. Okay. Then for the seventh one, A sub n equals 1. So the right side goes up. N is odd because it's 3. So that means the left side goes the opposite way of the right. So it goes down. And our y-intercept is 0, 4. So graph where the right one goes up, the left one goes down, and the y-intercept of 0, 4 is C. And then that really just leaves us with this last one. So the last one must be D, because that's the only graph that's left. But we can tell it's D for a couple of reasons. But the easiest reasons are A sub n would be 1 if you multiply this out, so the right goes up. N would be 4, so the left also goes up. And if we wanted to, we could find that there's an x-intercept at 2, 0. Right? Because if x were 2, y would be 0. And so that means that's D. Okay, so that's one of the things you should be able to do with the homework, is you should be able to pick out the correct graph from the equation. However, if you wanted to help yourself out, you could always graph these using class calc and then pair up the correct equation. Okay. So then the last thing in this section is solving polynomial inequalities, which we do basically the same way that we solved quadratic inequalities. We're going to graph it, and we're going to look for the part of the graph that fits the inequality we're looking for. So in this first example here, the part of the graph, what we're looking for is what we want to remember is that greater than 0 is on top of the graph, equal to 0 is on the graph, and less than 0 is below the x-axis. So in this case, we're doing less than 0, so we're looking for where is the function below the x-axis. So if we graph this real quick, and sorry, I already forgot what it was, x cubed minus 4x squared minus 20x plus 48. Okay, so let's zoom back in here a little. And so from the graph, we can see that it has x-intercepts at -4, 2, and 6. And then it goes below the graph, then above it, below, and above. So if I drew a really nice little sketch of this, what I would have is I'd have -4 over here, 2, and 6, and the graph would look like this. So I'm just drawing a little sketch because all I really care is where is it 0, and where is it above and below the x-axis. So the pieces where it is below the x-axis are over here on the left and in the middle here between 2 and 6. So the solution would be -infinity to -4 union 2 to 6. And notice I don't include -4, 2, and 6 because I'm not doing or equal to. Okay, and that's all there really is to doing these. So if we look at the second one here, we're going to do the same thing. I want to draw a graph. Greater than 0 is above the x-axis, equal to 0 is on the x-axis, and less than 0 is below it. In this case, we're doing greater than or equal to, so that's these two. So we're going to look for greater than or equal to. So we graph y equals x to the 4th minus 5x cubed plus 3x squared plus 15x minus 18. Okay. And so we end up with a graph that looks something like this. We get a negative decimal over there. Right, if I graph it, I had a negative decimal. I've got another decimal. I've got 2, and I've got 3 for my x-intercepts. Okay, so, sorry. 2 and 3, and then the other 2 were decimals. So I can draw a little sketch of this graph. Okay, and it's not going to be completely accurate, but it just will show me where it's above and below the x-axis. So I was below, I had an x-intercept over here, and then I was below. Then I hit the x-axis and went above. Then I went down below again at 2, and then I went up again at 3. Okay, and the parts of the graph we're looking for here is when is it above the x-axis or equal to 0. And so we can tell from the graph that my solution is going to end up looking something like this. Negative infinity to some number, bracket, union, bracket, some number, up to 2, bracket, union, bracket, 3 to infinity. So we know it's going to look something like that, but I have to figure out what those other 2 x-intercepts are. And that's where some of the stuff we've been doing earlier in this chapter comes in. So I can use synthetic division to factor out the 2 zeros I already know, and then I can find the other 2 using factoring or the quadratic formula or something like that. So I've got 1, negative 5, 3, 15, negative 18. So 1 plus nothing is 1. 2 times 1 is 2. Negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. 3 plus negative 6 is negative 3. 2 times negative 3 is a negative 6. 15 plus negative 6 is 9. 2 times 9 is 18. Negative 18 plus 18 is 0. So we factored that one out, and now we'll factor out the 3. So 1 plus nothing is 1. 3 times 1 is 3. Negative 3 plus 3 is 0. 0 times 3 is 0. Negative 3 plus 0 is negative 3. 3 times negative 3 is 9. Negative 9. 9 plus negative 9 is 0. And so that leaves me with x squared minus 3 equals 0, which we can solve. So add 3 to both sides and use the square root property. So x equals plus or minus the square root of 3. So that's what these other 2 intersects are. So this will be negative square root of 3, and this will be positive square root of 3. Okay, so that's the idea. So go ahead and pause the video briefly and try the other 2 here, and when you're ready, you can come back and we'll go through them together. Okay, so for this first one, when we graph it, we get a graph that looks something like this. Okay, and I know this intercept is 0. And so there's a couple of ways you can go about that, but if you wanted to do it exactly like the one above, actually, before I do that, we've got greater than 0, equal to 0, and less than 0, right? And in this case, we want to be greater than 0, so we're looking for just the top point. So that's this part, and this part is where it's greater than 0. So that's going to be blank, comma, 0, union, blank, comma, infinity, right? Because I need to figure out what those other 2 points are. So we could use synthetic division, and it would look something like this. So 1 plus nothing is 1. 0 times 1 is 0. 0 plus 0 is 0. 0 times 0 is 0. Negative 3 plus 0 is 0. 0 times negative 3 is 0. 0 plus 0 is 0. And so we end up with x squared minus 3 equals 0. And we solved this earlier up at the upper right of the screen right now. So that's going to be plus or minus the square root of 3. So this will be negative square root of 3, and this will be positive square root of 3. And then the last one, if you graph it, so y equals x to the third plus 7x squared minus 36. And when you do that one, if I zoom out here a little, you should get all the points from the graph. So we get negative 6, 0, negative 3, 0, and 2, 0. So its graph looks like this. So we've got greater than 0, equal to 0, less than 0. This graph looks like this. Kind of. So -6, -3, and 2. And in this case, we want to be less than or equal to 0. So that would be less than or equal to 0 would be those two pieces. And so that's below the x-axis. So those are over here. So that's -infinity to -6 union -3 to 2. Okay. So that's it for section 3.4. Make sure you're doing all your homework on my math lab. And if you have any questions, feel free to email me, text me, or call me.